Hey everybody, so I'm obviously not there today, but I want you to watch these notes. They're going to be on parallel circuits. We did series circuits last time. And after you look at these notes and listen to me talk, you should be able to figure out how to do the rest of the packet that involves the parallel circuits. So if you remember from what we did last time, we had series circuits, and in a series circuit, since there was only one loop in the circuit from battery to back to the end of the battery, the current had to be the same on every single resistor. And if the current was the same on every single resistor but they had a different resistance value, then that means the voltage had to be different. And the way you could calculate if what you did was right was by using Kirchhoff's voltage law, which said that if you add up the total voltage drop on each resistor, that should be equal to the voltage put into the circuit by the battery. Just a quick review, I'm doing it out loud. But now we're going to work on parallels. And in a parallel circuit, it's kind of the opposite. Instead of each resistor having the same current but different voltage, now since each resistor is connected to the same terminals at the top and the bottom, they're all connected to the same wire, they all have to have the same voltage. And if they all have the same voltage but different resistances, then it's the current that has to be different. And you should, again, now we're going to bring into Kirchhoff's current law, which says that if you add up the different currents in the parallel resistor, they should equal the total current coming out of the battery. But in order to solve these problems, we have to do the same thing we did for the series circuit, and the first thing we do is find RT, the total resistance, which is what you would get if you were going to replace all the resistors with a single resistor that had the same effective resistance. What would that be? For series circuits, that's very easy. You just add up the resistance. For parallel circuits, it's not that easy. It doesn't work like that. For parallel circuits, you have this reciprocal type thing. So it's 1 over R, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So what you're going to have to use a calculator for this. So you do, in this case, it would be 1 divided by 470 plus 1 divided by 2200 plus 1 divided by 3300, and you'd add those up. I'm not going to get into adding those up by hand because that's a big common denominator you have to find. You just do it on a calculator and you get some decimal answer. Then you take 1 divided by that answer, and that's going to give you the total resistance. And that formula is where it says RT equals. I usually do it in 2 steps. I do the 1 over R1 plus 1 over R2 plus 1 over R3, hit enter, get an answer, and then do 1 divided by that answer, and that gives me my total resistance. Okay, so this is just a reiteration of what I just said. For the parallel circuit, we're going to find things in this order pretty much. We're going to find the total resistance, you need to find the total voltage and the voltage across each resistor, and you need to find the total current and the current across each resistor. That's going to be, when I say solve a circuit, that's what I mean. And then we're going to use the results to verify Kirchhoff's current law. So we're going to make sure that each individual current through each resistor, when I add them together, it gives me the total current. And we're going to do it for that circuit that's down there. Okay, so the total resistance, like I said before, is going to be 1 divided by 470 plus 1 divided by 2200 plus 1 divided by 3300. Don't forget you have to convert these out of SI notation in order to properly use them. You get an answer, and when you do 1 divided by that, you should get 346.59 ohms. And what you'll notice here, and something that a way you can tell that your answer is correct, is if you do this correctly, the total resistance should be less than even the smallest resistor. Whereas in the other one, in series circuits, if you found the total resistance was greater than even the biggest resistor. This is the other way. By putting resistors in parallel, you've reduced the effective resistance. Okay, now it's easy to find the voltage across each component because in a parallel circuit, because each of them is connected to the top of the battery at the top and the bottom of the battery at the bottom. Because remember, any red wire, that's considered one point. They all have the same charge, so you don't consider where IR1 is to be a different point from where IR2 is. So the voltage across each one has to be 15 volts. So VT is 15, VR1 is 15, VR2 is 15, and VR3 is 15. Now we have to find the current through each component. And there I've shown you my little triangle there. I'm pointing to I, which is I is V over R. Now we already know the V, and we already know the resistance value, so we can find the current pretty easily. V over R is it's 15 over 470, which gives you 31.915 milliamps for R1. R2 is 15 because the voltage is always 15 on every single one of them. For parallel circuits, the voltage is the same. 15 divided by 2200 gives you 6.818 milliamps, and 15 divided by 3300 gives you 4.545 milliamps. This is converted into SI notation after you do the math. And I also find that if I did VT divided by RT, the total resistance that we found by doing the reciprocal thing, we're going to get 43.278 milliamps. Okay, and then we're going to do the last part is to verify that with Kirchhoff's current law, which is that if you add up the 3 individual currents for each resistor, that should equal the total current. So you can see that that works. It's 31 plus 6 plus 4 is 43.278. We found 43.278 when we found the total current by doing VT over RT. So we have the same thing, so we've checked it and we know it's right. Okay, so just to make sure everybody's on the right page, Kirchhoff's voltage law. The sum of all the voltage drop in a series circuit is the total applied voltage. That's Kirchhoff's voltage law applied to series circuits. Kirchhoff's current law says the total current in a parallel circuit equals the sum of each of the branch currents. So in a parallel circuit, you have different branches. The current should add up to the total current. That's in a parallel.